Yeah, so the talk is about the complexity of two-stage stochastic IPs. So of course you might wonder what are two-stage stochastic IPs, and we're simply looking at an integer program where we maximize some objective, and we have a constraint matrix, and we have lower and upper bounds on the variables. So the special thing about two-stage stochastic IPs is that the constraint matrix has a very specific structure, and it consists essentially of block submatrices, AI and BIs. So we have a vertical line of block matrices. These are the A matrices, and we have a diagonal line of B matrices. And actually, if you are familiar with stochastic programming, you might be familiar with those type of matrices. Actually, in practice, they are a very common tool to model processes over time. So, for example, they are used in the modeling of manufacturing processes, or in modeling energy consumption and planning ahead of time, or in chemical batch scheduling. The idea behind how you model these things is we have uncertainty over time. So we have a first stage that we know of, and this first stage is modeled by the A matrices. And then in the second time, there's uncertainty. So there is a possibility of n scenarios, and each of those scenarios is modeled by one of the B matrices. These are the matrices, the block matrices on the diagonal line. And what we would like to optimize the average outcome. Okay, this is done by the objective function for all of the variables. So this is kind of the story of these two-stage stochastic matrices, and usually they are stated in a stochastical way. But the way we do it is like we consider the so-called deterministic equivalent of the constraint matrix. This is kind of this huge matrix consisting of these sub-block matrices. Okay, and actually there is a lot of practical work to solve these type of IPs in practice, and usually also in the mixed integer setting. But what we will concentrate on is the worst case complexity, like to give a possibly good algorithm that runs well in the worst case. And actually there was also some work done by Hemmeke and Schulz. They proved that those two-stage stochastic IPs can be solved in time f of r, s, t, and delta, and polynomially in n and l, the encoding length. So r, s, and t are the dimensions of the block matrices, and delta is the largest entry of the constraint matrix. And the problem so far was that they use existential or finiteness results on commutative algebra to say just the existence of such a function. But actually no upper bound is known, so we don't know the exact dependency on the parameters of the running time. The only thing that is known regarding the function is that using their methods, there is at least an Ackermanian dependency on the parameters. So actually, we know that on the minimum, we know that the function already grows extremely fast. Kind of the strange thing is, like, there's a very related class of IPs, which are called n-fold IPs. You may have heard of those. And they are very similar because the constraint matrix is just the transposed matrix. And over the last few years, there has been several papers, and I just mentioned all the authors kind of that took part in that research. It was quite a few, and kind of the best known running time that we know for n-folds is delta to the order of r squared times s. Okay, so those essentially can be solved very efficiently by a decent exponential term. And so the surprising thing was, like, you transpose the constraint matrix, and why are two-stage IPs so much harder? But that's how things are. And in this paper, kind of, we try to improve upon the upper bound. Okay, so the way those IPs are solved, like n-fold and two-stage, is by considering the so-called Graver complexity of the constraint matrix. So what is the Graver complexity? Essentially, you consider integral elements of your kernel, and you say that an element like an integral kernel element is a Graver element if it cannot be decomposed in a sign-compatible way. So geometrically, those elements are just your inclusion-wise minimal elements of your kernel. And what you would like to bound in order to get an algorithm to solve your IP is just bound the size of every Graver element. So like the infinity norm or the one norm. As soon as you can do that, then you can use a more or less standard augmentation framework. Okay, so let me briefly explain how that works. So the idea is we start with an initial feasible solution X, and then we would like to improve upon that solution stepwise. So what we do is we would like to find an element of the kernel, an integral element, of course, with improved objective. So now, how can we compute this kernel element? Is we can just use a dynamic program to search the whole area around, okay, around zero, and see if if we use the bound of the Graver elements, and then we know, since all Graver elements are bounded in size, we know that if there exists an improving element in the kernel, there also exists a Graver element that improves upon the objective. So we can use this element, so we are guaranteed to find one in the area because the norm is bounded. And then we just add multiples of this element to our current solution and improve it. So multiplicity depends on our current bounds. Okay. But we are guaranteed, as long as we are not optimal, we will always find this improving, augmenting kernel element. Okay, so essentially the only thing that remains to be done is, like, how can we improve, how can we prove a bound on the size of the Graver elements? That is, by the way, also what Hemmeke and Schulz did. And for the upper bound, for the proof of the upper bound, they used this algebraic methods. Mm. Okay. So here is our main lemma. So this is also kind of what I like about integer programming. Like, if you just dig long enough, you will end up kind of with some very nice combinatorial problem. And that's what I have to solve. And sometimes this is known, and in this case, I haven't found anything. Also, it feels like a very intuitive lemma, but I didn't find anything, so I proved it myself. So the lemma states that we are given multisets, n multisets of vectors. Mm-hmm. And the norm of the vectors in the sets is bounded by delta. The infinity norm is bounded by delta. And we also suppose that the sum of all the vectors within each set sums up to the same point in the space. Mm-hmm. Okay, so I have a picture like this looks on the left picture here. So we have each set, and a sum of vectors, and all sets sum up to the same point B in the space. And then the claim is that there always exist sub-multisets S1 to Sn of the Ti's, and the size of the sub-multisets is always bounded by the parameter, so by the dimension and the norm of the vectors, delta. And they also sum up to some smaller point in the space. Mm. Okay, so the important thing to notice here is that the bound on the cardinality of the subsets does not depend on n, and it also does not depend on the size of the Ti's, so on the cardinality of the Ti's. Okay. And we will see this lemma rather directly gives us a bound for the graver elements of two-stage IPs. So the geometric interpretation of the lemma is as follows. So here we have our T, our vector sets that sum up to the same point B. Now the lemma states that we can permute those, like we permute the order of each set such that we find a point B prime of bounded size, so that all sets sum up to this earlier point B prime in the space. Okay. So B prime doesn't necessarily have to be on the line between 0 and B, but it can be somewhere. Okay, so I hope you have an intuition for the lemma now. So why does this lemma actually imply a bound for the graver elements? I will try to give you some intuition. So suppose we have our vector G, our kernel element, integral element in a kernel. And if it's too large, we would like to decompose it. So we want to show that there exists a decomposition. And what we can do now is, like we split the vector into sub-vectors that belong to those sub-matrices. So A1, B1 is just this sub-matrix, and A2, B2 is this sub-matrix, leaving out the zeros. Okay. And then we have on the right side the corresponding sub-vectors of G. Okay, so G0 is always on top because those belong to the A matrices. And then we have Gi, which corresponds to the respective B matrix. Okay, and now we know, since those block matrices have bounded dimension, we know that a decomposition of those graver elements exists. Okay, like this is a classical result. So we can decompose those into smaller kernel elements, but now the kernel elements only refer to the block matrices. AI, A1, AI, BI. Okay. So now we can decompose those into those graver elements. And what we would like to do now is we would like to put them back together in order to obtain a graver element for the whole two-stage matrix. So what problem occurs now? The problem is that we might have different values in the upper part. You know, like the upper part always corresponds to the variables for the AI matrices. So theoretically, what would be good? Like it would be good if we would have, for example, the first vector where we have always the same entries in those subvectors here. Then we would not have conflicting assignments for the G0 variable. And then we could construct a graver element for the whole two-stage stochastic matrix. But of course, in general, we cannot assume that this is the case. So what would we like to do? We would like to find subsets of the respective decomposition that sum up all to the same value. So in case we find subsets
such that the upper part of the vector that corresponds to the A matrix, always have the same value. We do not have conflicting assignments for this variable. Okay, so this is what we actually like. We would like to find those subsets such that the sum of the upper part is all equal. And this is just what the theorem says. Remember, we have the sums of the upper part, they all sum up to G0 anyway. So this is our assumption to use the lemma. But then we always find small subsets so that also sum up to the same value. This is what the lemma states then. So we can use this, and based on the lemma, we just use those subsets that we get out of the lemma in order to construct the decomposition. So we find a smaller element that is really less equal than G. That is also a kernel element. Okay, so we are guaranteed we get the bounds from the lemma in order to construct the smaller graver element. Okay, so this directly gives us an algorithm to solve the two-stage stochastic IP, and the running time that we obtain is double exponential in R and S. And S is the number of variables of the A matrix, and R is the number of variables of the A matrix, and S is the number of rows of the A and B matrix. T is the number of variables of the B matrix that now only occurs polynomially. So the running time in total is only polynomial in N and T, and the encoding length L. So this is a double exponential bound, but we probably cannot improve upon it. So it's still worse than n-fold if you compare, but it seems like those kind of IPs are definitely harder to solve than n-folds. So now I would like to give you a brief overview on how we can prove this lemma actually. So if we consider we are in dimension 1, like this is actually the easy case. So we have given classical multisets, and every entry is bounded by delta, and they all sum up to the same number. Then we can find subsets, like bounded subsets by delta times delta factorials, such that they all sum up to the same value. This proof is actually rather easy to see. First, we consider an even simpler setting. So suppose we have now only multisets that only consist of the same number. Okay, so multisets that only consist of number 2, and multisets that only consist of number 3, and so on. Then it's easy to find subsets that all sum up to the same value. Why? We just take the least common multiple. In that case, 2, 3, and 4, which is 12. And we know we can construct those subsets of these sets above here to construct the smaller subsets. Okay. And now we can see that we can reduce the general case actually to this case. Why? Because if the sets are sufficiently large, let's say larger than delta times delta factorials, then we just pick those subsets for the number that occurs most of the time. Okay, so here we have 3 that occurs 4 times, so we choose the subset that consists only of 3s, and so on. And then we apply the previous technique of taking the least common multiple. So the one-dimensional case is rather easy to see, but the problem starts already in dimension 2. So the question for me was kind of how, like, this one-dimensional technique should generalize somehow to the more dimensional case. But if you think about like taking least common multiple of vectors, doesn't make any sense, right? I mean, those vectors might point into different directions. So what is the least common multiples of vectors? But vectors, we will see, is actually not the right way to look at the higher dimensional case. So for the higher dimensional case, we consider the linear program. And the linear program is just a different way of writing the sets. So XP just states the multiplicity, how often one vector occurs in a set. Okay, and then P is every possible vector. So every vector that is bounded in the infinitor norm by delta. There are only parameter many. Okay, so we know each set Ti actually corresponds to one feasible solution of our linear program. Okay, just by choosing lambda I as the multiplicities and how often one vector occurs in our set. Okay, so what we're doing now is, like, how can we state solutions of the LP in a different way? From basic LP theory, we know that every LP solution is just a convex combination of all possible basic feasible solutions of the LP. So what we're doing now is we're writing the lambda i's, so the representation for our sets Ti, we write those as a convex combination of basic feasible solutions. And then we're just picking one basic feasible solution out of those. And we pick the one just with the largest coefficient, so with the largest gamma I, okay? So the gamma I sum up to 1. And we know that the number of basic feasible solutions of the LP is not too large, it's only parameter. Why? Because we have a bounded number of variables. Okay, this only depends on delta to the power of d. And we have only d many constraints. So the number of possible basic feasible solutions is just parameter. It's exponential, of course, but it's just depending on the parameter. And then we're just picking that basic feasible solution with the largest coefficient in the convex combination. So if you think back to the one-dimensional case, here we just picked one number of our set, right, as a subset. This is now equivalent to picking one basis, but of the convex combination. So the generalization to the more dimensional case is not considering vectors, but we're considering basis of our LP. And then it also makes sense to think of the least common multiple. So what we can now restrict to is we consider basis, and we would like to have the following. We would like to find vectors, so we multiply our basis by vectors, such that they all sum up to the same point. The advantage we now have is we have only parameter many different sets. Okay, because the number of bases is bounded by the parameter. But now we would like to find those y vectors such that all bases kind of intersect in this single point. And what this problem actually is, it's just intersection of integer counts. And the integer counts have our basis from the basic feasible solution. So what is an integer count? Let me just briefly tell you. This is just like putting all possible positive vectors and multiplying by b. Okay, so you can think of a lattice, and the integer count is just the positive orthant of the lattice. And now what we need to argue that this intersection behaves actually nicely, like we don't get a too fancy basis. Like if we intersect two integer counts, the coefficients of our new basis do not explode. But this we can show by the Steinitz lemma actually. Maybe you have some intuition for that. but I cannot go into the details here. But actually we can do this. Like we have two integer counts. The intersection of two integer counts is again an integer count. And the coefficients are only parameter again of the new basis. So geometrically, that looks something like this. Like we have the green integer count and the black integer count, and the intersection, like is here the red point. And of course, this repeats in the same way. So we get intersection is again an integer count. Okay. In this way, we go back to the one-dimensional case. Like now we see why, in what sense the one-dimensional case made sense. The least common multiple is actually just an intersection of integer counts, of one-dimensional integer counts. Like we consider the integer counts of a number A and the integer count of a number B. And then we know that the intersection of those is just the integer count of the least common multiple of A and B. So this is kind of where things come together. Of course, I didn't go into every detail. So if you really work out every detail, things come a bit more complicated, but I hopefully could give you an intuitive point of view of how to prove the lemma. So there are some open questions. So actually, I thought I had proven a lower bound, or we here in Kiel had proven a lower bound also for the complexity of solving two-stage IPs, but there was a mistake, so we are currently not too sure if it holds. So the question is, of course, like, is the running bound, is the running time tight? And I didn't say anything about multi-stage IPs, but our techniques also generalize to the multi-stage setting. And probably one of the more important open questions in block IPs is, can we solve so-called 4-block IPs in FPT time? So 4-block IPs is just a mix of both of two-stage and n-folds, where you have a horizontal block line of matrices and a vertical line and the diagonal line. So this kind of generalizes those two. And we do not know if we can get an FPT algorithm there. Also, like
Kim?
Yeah.
We need to allow some time for questions.
Oh, I'm sorry. Am I already over time?
Yeah, a little bit. Do you have any more slides?
No, that was the last slide. I'm done.
Oh, okay, good timing. Okay, if anybody has questions, please unmute yourself and go ahead.
So, can I ask a question? Hello?
Yeah.
Hello? Oh, hi. Thanks for the nice talk. So, in your lemma, suppose if you look at kind of the optimization version, where I want to find the smallest bound on the n subsets that give me the same sum,
Okay.
I presume, what's the hardness of that? And do you know, probably it's hard. Is it can you find an approximation of it?
Oh, that is a good question. I didn't think of it, to be honest.
All right, thank you.
I would guess it's hard, but I really didn't look
Yeah,
at it.
I would guess so, but I was wondering maybe if you can give like an approximation bound or something.
Yeah, good question. Like I have no idea, to be honest.
There's a question by Joe Pat. I can repeat it for him. What do you think is the optimal dependence on n?
On n, actually we have, like in the paper with Eisenbrand and Kotecki and so on, we state, I think, like that what mainly Martin did, but I think it's linear in n and some logarithmic terms.
Mm-hmm.
So you surely cannot improve upon the linear term. but we are pretty tight in that case, in the dependency on n, I think. Basically, but we have to assume that we can solve the LP relaxation of the problem, and that we don't know yet if that can be done in linear time.
Mm-hmm.
And there's also a raised end.
Sorry, can you repeat?
No, I was telling Dan that there is a raised end.
Yes, I have a quick question. It's sort of just my curiosity. So obviously there's been some really interesting recent work involving parallel machine scheduling with n-fold, n-fold integer programs. Have you thought about if there's any kind of way we could use, say, this particular IP, or is there any kind of intrinsic meaning that maybe might come out of, say, this IP? Because sometimes there's machines that there's constraints you want to impose, and sometimes just having it in the classic way, like the assignment IP, or I'm getting a little technical, but have you thought about any kind of relation between, say, parallel machine scheduling and, say, this IP, or any relation, like, say, some of those packing problems?
Yeah, no, very good question. Kind of that's what I have thought about, and also I know of Martin Kotecki, who thought about that for a long time. And he has some applications, and it feels like there should be a lot, but it feels like we haven't found the right algorithmic application for those kind of IPs. In n-fold, you're right, we had a lot of success with those scheduling IPs and social choice and so on, but we're very surprised. Like, I'm citing Martin again, who said, like, it feels like we have a huge hammer with those two-stage IPs, but we don't know where to hit.
Gotcha. Yeah, no, I got you. No, excellent. Thank you.
I don't see the raised hand. I'm sorry. Somebody said that there was a raised hand, but I don't see it.
Oh, I removed it now. I lowered it now since it was done, but it's under participants. You will see them.
Yeah, but I wasn't seeing it. Okay. All right. Well, we are at the end of this talk. When we should move on to the second talk. First, why don't we applaud Kim-Manuel, and congratulations on winning the Best Paper Award again.